This clutch is not for the family sedan. It's a racing clutch designed for a car with an 1800 horsepower engine. Without this kind of heavy-duty clutch, there would be no way to transfer that much power to the wheels, and the race car would be going nowhere fast. Race cars use a manual transmission to transfer power to the wheels, so a good clutch is behind every win. Production starts with the flywheel, which connects the clutch to the engine. Computerized cutting tools shape this aluminum part, then move on to carve the cover plate for the clutch. They trim its perimeter to give it the correct profile and reduce its weight. Next, they use a bolt with an industrial diamond tip to level the surface of an iron friction disc. This will allow for better contact with other parts of the clutch. There are typically 2 to 3 of these friction discs in a racing clutch. The clutch discs will ride against this steel insert, which they position on the flywheel. The technician applies locking compound to bolts, then uses them to attach the insert to the flywheel. Here, the technician sets the bolts to a precise torque. Next, he uses this grinder to flatten the surface of the steel insert, again for better contact with the clutch disc. These bolts will anchor the clutch assembly to the flywheel. They're called stand bolts, and there are 6. Here, they sculpt titanium cylinders to act as stands for the bolts that were just installed in the flywheel. Titanium is strong and lightweight, which is important because of the huge amount of energy the clutch must transfer. The technician places a stand over each bolt, then arranges the clutch discs and a floater plate on the flywheel. He presets the height of the stands. Then he prepares the pressure plate assembly. He presses aluminum cups into holes in the cover. These cups will hold springs that will be used to change the pressure of the clutch pack. But he holds off on inserting the springs in the cups. First, he installs a series of levers on the cover plate. He slides pivot pins into each lever. These pins will enable the levers to compress and decompress the clutch pack. He applies lubricant to adjuster screws for the clutch springs, then threads each one into an aluminum casing. He inserts an assembly in each cup, followed by a heavy-duty spring. He now installs the pressure ring on the underside of the cover. When the driver releases the clutch pedal, the levers cause the pressure ring to compress the clutch pack. That action transfers power from the engine to the transmission. He now slips the pressure ring assembly over the stand bolts and secures it with nuts. He adjusts each stand with a socket wrench, then checks the height. He measures the tips of the levers to confirm they're even and makes any necessary adjustments. He pushes the levers to test this clutch, and the pressure ring responds as it should, creating the necessary pressure on the clutch pack. Finally, a certification sticker and some strapping to secure it for shipping. At the track, this clutch will be serviced between every run. And if it's operating at peak performance, a win could be just down the road. Drinking water that's fresh, clean, and crystal clear is something many of us take for granted. We might not give it a second thought, but between the source and our tap, a lot happens to make that water fit to drink. Our water may come from Mother Nature, but it's far from pristine. It starts its journey to the treatment plant through a water intake pipe. On the wall of that pipe, about 6.5 feet down, is a 6-inch hole. Covering that hole is a metal grill designed to keep out large debris such as tree branches. The water flows to the pumping station, where it goes through a preliminary screening. A giant revolving screen removes fish, garbage, and grass. Once they remove the debris, a low-pressure pump moves the water into the treatment plant. The untreated water, called raw water, is dirty and smelly. They first add a powerful form of the chemical element carbon, called activated carbon. It absorbs contaminants such as solvents and pesticides. That rids the water of bad taste and odor. From there, the water goes through a series of mixing tanks. The first tank holds a chemical called aluminum sulfate. It acts as a coagulant, a substance that thickens liquid into globs. In the raw water, the aluminum sulfate forms tiny sticky globs called flocks. Bacteria, mud, and other impurities stick to those flocks. Then the flock-filled water moves on to the second mixing tank. The second tank holds a chemical called polymer, which is essential to the next step of the process, called sedimentation. 5 pipes inject the water with superfine particles of sand, called microsand. The polymer coats the sand, making it sticky. The grains of sand then stick to the flocks in the raw water, weighing them down even more. The water then flows into a settling tank, where the flocks, because they're heavier, settle to the bottom. You can see the result in this demonstration. The water is finally clear, but it's far from drinkable because it's still full of bacteria, viruses, and other organic matter. So on to the next step, filtration. The water flows onto the top of the filter, then trickles downward, passing through a layer of anthracite, a type of coal, then through a layer of sand. This filters out any remaining particles, which then flow to the middle. But the water is still teeming with bacteria and viruses, so it has to be disinfected. They add 1.9 milligrams of chlorine for every 4 cups of water, enough to kill off those germs and bugs. Then they add a mineral called silicate to prevent calcium buildup from blocking our water pipes. The treatment plant sends water samples to a government inspector, who continuously monitors the water supply to ensure it meets safety standards. The amount of chlorine remaining in our drinking water is 20 millionths of an ounce per liter. The chlorine gas the plant uses is highly toxic. Should any leak out, emergency teams would have to evacuate a 6-mile radius. So the plant stores the drums of chlorine in a high-security area. It's taken about 45 minutes to turn raw water into treated water. Now, these electric motors will pump it through underground pipes right to your tap. Almost every culture has used drums in some way. Drums have been a part of different civilizations for thousands of years. The earliest drum shells were hollowed out logs or gourds. Different sizes created different sounds. Today, drum shells are more sophisticated and consistent. To make drum shells, they slice an enormous rock maple log into several boards. Maple is ideal for making drum shells because its hardness allows sound to resonate fully. Each of these maple boards will be transformed into one drum shell. Workers feed the boards to a ripsaw, which cuts them to the correct width. This varies depending on the size of the drum being made. Then each board goes into a planer, which shaves it thinner. A worker aligns the board with markings on a saw table. This positions the board to be cut to the correct length. A radial arm saw does the job neatly. Now he sizes up each board in preparation for tapering. He places a board on an angle in a jig, and then moves the end against a router cutter to taper it. It takes a few passes to get it just right. The taper needs to be about 6 inches long. He thins the other end of the board to the same dimension. These tapered ends will make it easier to bend the wood into a drum shape later. They'll also act as scarf joints, which will fasten the ends of the board together when it's bent round. But first, this board needs some softening up. An hour in the steam box does the trick. It's pliable enough to wind around a hot cylindrical form. Steel banding secures the board to the bending form where it will spend 10 to 15 minutes. A worker pries apart the ends and applies a generous amount of glue between the tapered tips. Then he removes the shim that was holding the ends apart so that they stick together. He places a wooden guard over the glue joint. This nylon mesh band is a clamp. He wraps it around the drum shell and turns the screw to pull the band tightly around the wood until it reaches 14 inches in diameter. Then he fastens over a dozen steel clamps onto the joint. All these clamps will prevent any gaps from occurring in the joint as the glue sets overnight. With the joint sealed, the drum shell now spins, while a cutter shaves down the edges to make it a true round shell. Then they bring in another cutter. It bores into the shell, making a smooth edge and rounding the inside. He turns the drum shell around to cut it from another angle. As the shell spins, a high-speed cutter shaves the outside from top to bottom. This makes the surface very smooth. It takes about a week to make a drum shell from solid wood, and it will be able to stand up to some loud playing. There's more than one way to beat a drum, and there's more than one way to make one. Earlier, we showed you how they create a drum shell from a maple plank. But a newer technique involves layering multiple plies of wood. This process is called laminating, and you can hear the difference. The laminated drum is an instrument of change. Its sound is crisper than a drum crafted from a single piece of wood. To make one, they layer 11 sheets of maple. Here, a worker glues on the final ply using a special adhesive. This outer layer is a luxurious bird's eye maple. Rollers press all the layers together to ensure they stick without any gaps. Then they cut through the overlap to create a perfect seam. A robotic drill now takes over. It drills holes of various diameters. The small ones will hold hardware. This larger one is an air vent. A computerized router then cuts the bearing edges to a 45-degree angle, and a worker sands it smooth. He uses a level surface to ensure that all the edges are perfect. If they're not, the drum heads won't fit properly. He applies an adhesive to the air hole and inserts a plastic vent. Next, he inserts brackets called lugs into the other holes and screws them in. There are 10 lugs spaced 36 degrees apart. They'll hold the rods that will attach the heads to the drum shell and also enable the drummer to adjust the tension on the heads. Here, he attaches a lever to control wires called snares that are to be strung across the bottom head. It's called a snare strainer. Then he fits a plastic drum head over the bottom of the shell. The counter hoop goes on next. It has little tabs which he aligns with each lug. He slides tension rods into the holes in the tabs. Using a drum key, he tightens the head to an even tension across the shell. Now he blasts it with a heat gun to shrink the plastic and remove any wrinkles. Now he places another plastic head on the top bearing edge. Since this head is the one that gets played, it's twice as thick as the bottom one. He places the chrome rim on it and tightens the tension rods. These brass brackets will hold the snare wires. He slides them under the snares that are stretched tightly across a jig, putting one at each end. He measures the length, then solders the snare wires to the brackets. He snips the wires on both ends and unlocks each wire from the holding device. When he removes the snares, they're held together by the brackets. He slides a nylon strap into one of the brackets, then attaches the strap to a fixture just above the bottom head. The other end of the snare is attached to the strainer, the lever that will apply tension and release it, controlling its distinctive buzz. For a bigger sound, there's the bass drum. It's made with wooden hoops. They attach the hoops to the drum shell with steel claws. As they screw the claws to the hoop, the drum head is pulled just tightly enough to produce that low-pitched bass drum sound. Now it's off to be played. Electric motors are made of two main components, one stationary called the stator, the other a rotor that moves inside the stator. The stator has multiple wire coils. Running electricity through them creates a concentrated magnetic field that turns the rotor, creating mechanical power. The stator is lined with slots, each of which holds a copper coil. The more powerful the motor, the bigger the stator and the larger the slots. The first step is to line the slots with insulation. This insulation will keep the voltage confined to the coils. The coils are made from several copper wires wound together by programmable machines. The bigger the motor, the more wires per coil. In this motor, each coil consists of 13 strands of copper wire. Now, workers tie the coils. This prevents the wires from unraveling while being inserted into the stator slots. Workers cap each coil with fiberglass insulation. Then they insulate the portion of the coil left outside the slots with fiberglass sheets. Fiberglass wedges are inserted, locking the coils inside the slots. Once all the coils are inserted and insulated, workers begin preparing the connection. They slip an acrylic insulation sleeve over both ends of each coil. 13 coils, 26 ends. Then they group these insulated wires into large power cables. The number of wires per cable varies according to the speed and voltage of the motor. They solder the grouped wires together, then insulate the cables. They tuck some inside the stator and leave others accessible to be attached to a power source when the motor's installed. Now, using a cord made of heat and chemical-resistant polyester, they bind the coils tightly to ensure they won't move when the motor spins. This unit of bound coils is known as the stator coil. They now submerge the stator in a polyester-based varnish and vacuum it right through. This thorough penetration makes the stator coil moisture-resistant. The stator is put into an oven for 6 hours at 280 degrees Fahrenheit. The varnish hardens, making the stator coil rigid. Now they have to balance the rotor. If it's off-kilter, the motor will vibrate, hampering performance. They balance it the same way a mechanic balances car tires, only with 100 times greater precision. Now they slowly slide the rotor into the stator. Careful not to damage the stator coil. The rotor will turn on steel bearings. They heat these bearings to expand them, so they'll install easily. Then they blow on cold air to shrink them to a tight fit. It's the same process with the motor's back cover. Now, they heat the fan and install it over the back cover. The fan's job is to cool the running motor so that it doesn't overheat and break down. They cover the fan with a safety guard. Then install a cover on the front of the motor as well. They run the finished motor through various tests to assess, among other things, insulation strength and performance. These industrial motors are designed for use in factories, for running machinery such as conveyor belts, pumps, fans, and compressors. The invention of the electric violin was all about turning up the volume. It was back in the big band era, and the sound of the traditional violin was overpowered by the horns and drums. Amplifying the violin changed everything. Suddenly, the violin wasn't just a background sound, it was part of the show. The wired violin comes in different shapes because it doesn't rely on the body to resonate sound. This craftsman builds his electric violins one piece at a time, starting with the neck. He traces the shape onto a piece of maple. Then he outlines the top plate. He uses walnut for the lower bout or bottom part, as well as for the backbone of the violin. Next, he cuts out the shapes using a bandsaw. His goal here is to be very precise, because the closer he gets to the outline, the less sanding he'll have to do later. The dimensions for the top and neck are exactly the same as a traditional violin, so there won't be any difference in the reference points the violinist relies on. The lower bout is very stylized, and the head is more streamlined than a traditional violin. There's no decorative scroll. Next, he chisels out a cavity in the head of the violin to create the peg box. He carves parallel grooves onto the back to give it a snazzy look. Using a rasp, he shaves the wood to the correct thickness. He drills holes for the tuning pegs into the side of the peg box, one for each of the 4 strings. He files down the grooves on the back a little more. Then he scrapes the rest of the neck to give it a final finish. Using a reamer, he tapers the peg holes. The ebony pegs have matching tapers so they fit snugly into the holes. He checks to make sure everything measures up. Now he brushes wood glue onto the next section and presses the ebony fingerboard onto it. He wraps them with surgical tubing to hold them together while the glue dries. He drills 2 assembly holes in the top piece and makes corresponding holes in the other parts. He smooths the edges of the backbone with an oscillating sander. Then, using a high-speed router, he bevels the lower bout piece to give it a clean edge. He rubs teal-colored stain into the wood because loud colors seem appropriate for these high-volume instruments. A crystal has been glued into the violin's wooden bridge to generate electricity from the string's vibrations and create sound. He pulls the wire from the bridge through the backbone and then mounts the bout to the backbone. He bolts an ebony chin rest on top. Next, he attaches the neck to the rest of the assembly. He loops on the ebony tailpiece. He pulls a string from the tailpiece to a peg. The act of tightening the first string raises the bridge, which will be held in place only by tension. Now it's time to hook up the violin to the amplifier and let the music tell the rest of the story.